morning and welcome to IBHS Live Wildfire Fuel Breaks. We're here in the IBHS Large Test Chamber in Richburg, South Carolina. I'm Christina Grob, joined by our Senior Director for Product Design and Lead Research Meteorologist, Dr. Ian Jamanko. Ian, it's an exciting day here at IBHS.
Yeah, welcome inside our large full-scale test chamber today. We get to bring you inside some of the science we're doing here, focusing on wildfire today.
Absolutely. So this facility is very unique. It's the only place like it in the world where we have the capability to reproduce Mother Nature's hazards in a controlled, repeatable manner for science. And the insurance industry made this investment more than 10 years ago to build this facility and give us this capability so we can understand how to reduce the impact of events like wind-driven rain, hail, and wildfire, which is our focus today in communities across the country. Very important, Ian, as we do have a number of active wildfires tragically impacting communities across so much of the West right now.
That's right. I mean, we saw during a recent heat wave that's really still ongoing in the western third of North America. I don't want to even just say the United States. We are seeing a lot of impacts from fires, a lot of new starts, both lightning-related, human-caused. We have a lot of dry fuels out there thanks to the drought that's been prolonged now for some time in that part of the world. And what we're doing today behind us is just going to underscore the need for research and how we can take science, turn it into action, and ultimately really start to stop that chain of problems that we see happen time and time again.
Absolutely. We're excited to take you behind the scenes of how the research happens. We've got a very passionate team here at IBHS, and we're going to show you how our scientists do this work every single day. But this work in the test chamber is not the end of the road for this research. It has to leave Richburg, South Carolina, go out into these communities to make a difference. So we're excited to show you this part of the process. We've never done this before, so it's a huge opportunity to show people a little inside look at how we do our work.
That's right. So let's start with a look at who we are at IBHS. Yeah. We are a nonprofit research and kind of communication advocacy group. Our real goal is to use science to stop that cycle of destruction, displacement, that often accompanies severe weather. And we talk about weather as a whole, so wildfires included in there, severe thunderstorms, hurricanes, tornadoes. And the centerpiece of this is the building we're standing in right now. And you're seeing some of the kind of highlights of those kinds of tests that we've done here at IBHS in this facility. We do lots of other small laboratory work, but the centerpiece is this facility.
It's unique. The insurance industry, the property insurance industry, made this investment in resilience so that we can start to figure out how to bend down the risk curve. We're talking about turning the knobs. We're able to control things here. Ian, you and I both meteorologists by our background. This is the one place where we can control the weather.
Yes, everybody thinks we can control the weather as meteorologists, but right here, we can actually do some of that. We can turn the knobs. We can punch up, say, a hurricane eye-wall wind record and run it on an actual home. We can go simulate an ember storm that attacks a home in the wildfire space. We can go put a hailstorm on a building. We can do all of this. It lets us take one variable at a time and work the science problem to figure out the components and that chain that matters. And ultimately, you get to building system performance. That's kind of the ultimate goal, and turn that into actual action, not only for homeowners, the building industry, obviously our membership in the insurance world, to be able to understand that cascade of damage and how we stop it. How do we stop that chain?
That's right. So the test you're going to see today, there's going to be two of them. We're going to take you through 2 runs of a fuel breaks test right behind Ian and I. You can see where the pine straw is already laid out. That's the fuel we'll be using today. We'll introduce you to some of the passionate scientists that we work with right here at IBHS. And we're going to talk a lot about why all of this work matters, because it really drives our research day in and day out. And so to begin, we're going to check in for our first time today with our field reporter for the show, Armand Brody, one of our product developers here at IBHS. He is on the other side of the test chamber. It's a large facility, so we have space to spread out here. And he's got a check-in of why, Armand, we're doing this today.
Thank you, Christina. Yeah, this is a pretty big day for us. We are excited because we're doing research that matters. You heard Christina and Ian talk just a moment ago about the wildfires that are impacting North America. And we here at IBHS get to take these deeper dives into the science. And it's my privilege to sort of walk you through both tests. As you heard Christina mention, there are 2 tests today. So once we get done with test one, do not go away. Another test will be on the way. You will hear from Dan Gorham, our research engineer. You will also hear from Sean McComber, our construction and facilities manager. We will talk about why this research matters so much. We will also talk about how we do this kind of test, what goes into it, the process, how we prepare to make this science happen. There's an amazing relationship, this harmonious relationship between the research we do here and what we see out in the field. So there's this back and forth, and this chamber allows us to do that research at an enormously high level. It's something we're very, very proud of, something we're very, very excited about because we're doing quality work that matters. And so it'll be my privilege to walk you through sort of a play-by-play of both of our tests today. As I mentioned, test one is coming up shortly, but after test one, do not go away. We will have a second test later on. That's an early report from out here in the field. Let's send it back to Christina and Ian. A great day ahead of us.
Thanks, Armand. And we are going to bring you that coverage throughout the day today to really show you how the testing works, how research happens. These are scientists that work here every day, and we're excited to show you how everything breaks down.
That's right. We're going to take you, this is live science as it happens, and we're going to show you this experiment today looking at wildfire and the fuel breaks. So that's gaps in the fuel, and we'll get to some of the descriptions. But this is work that's been going on now for several weeks here in the IBHS Large Test Chamber with our research partners. So we've had a lot of folks on site. The United States Forest Service is a very big partner in this particular project. And they've been all working over the past several weeks right here to do this work and methodically going through these sequences, turning the knobs, moving one variable at a time, repeating the test, trying to see what are the key components, changing the wind speeds. So we're going to talk a little bit about that. We're going to bring Faraz Hediati in here in a minute. He's one of our wildfire specialists.
Yep.
So a lot going on here.
That's right. Tall Timber's another one of our collaborators on this project that, again, has been going on for weeks. We'll show you two tests today, but the true research project spans many more test runs than that. Research takes time, but we're excited to have the cameras in here today to show you how that all works. Now, this isn't the first time we've looked at fuel spread. You know, spread deals with the flames, in this case, more than the embers, which we also talk about embers because they are so important. Embers, of course, responsible for up to 90% of home ignitions during a wildfire. But today's focus is on fuels and the flames.
That's right. Several years ago, we started out looking at how fast fire can spread through these fine, dried fuels. You know, how fast does it happen under whatever wind conditions? We even went all the way back. You know, our initial research program focused on the ember attack on a structure. As we kind of work our way through the wildfire problem, we'll let Faraz explain a little bit of that in a minute, how we went from ember attack, covering all the bases of fire, ember attack, the wall of flame and how flame spreads across those kinds of components. So we're trying to tackle all of it.
Well.
Yeah, and the radiant heat component too, and looking at building materials and what are the temperatures and heat fluxes, the amount of energy that's imparted on that material to get it to ignite. So we're kind of tackling it, you know, one at a time, but all these components during a wildfire event, they're all working in concert to start kind of that cascade of damage.
Absolutely, and all of these things that we look at have immediate translations out into the field for whether it's homeowners or, in this case, firefighters who use fuel breaks. Fuel breaks can sometimes occur naturally, but it's also a technique that firefighters use. So this research quickly can have an impact.
Yeah, so one of the components, if you think about fire and its containment, we often see the percentages of a fire being contained. Well, one of those elements is the fire services basically cutting those breaks in the fuel. And so there's a couple components here. There's that one that we could easily provide an immediate benefit in terms of this type of research as to how wide do these gaps have to be given a certain set of environmental conditions, wind, humidity, those kinds of things. And then if you flip that around, there's also how we use and how we landscape, how we use the land around our homes and businesses. That's the ultimate part also where this goes into the guidance for just you and I as homeowners and folks who live in wildfire-prone areas.
That's right. So the distance of the fuel break is what we're going to change during the two tests today. We mentioned our research collaborators on this project, the U.S. Forest Service and Tall Timbers. We want to take a moment and talk with one of our research collaborators from the U.S. Forest Service about why we work together. You know, this problem we've talked about in wildfire, it's an enormous problem, and it takes a lot of great minds to help solve it. And we're excited to have some of these collaborators with us.
Yeah, we've got a great partnership, and the Forest Service, the United States Forest Service, has been with us every step of the way, along with the National Institute of Standards and Technology, that's NIST. Christina mentioned tall timbers also playing a role here. All of this coming together to one, do the work that we need to, both here in the IBHS laboratory, field observation, small laboratory testing. All of those things are really coming together to achieve results and turn that into action ultimately. So we are very fortunate. Dan Jimenez from the United States Forest Service is actually with us back there. Dan's back in the back helping out with today's test. He's been here on site for quite a while. But our own Aubrey Marcinko caught up with Dan and take a look at how Dan describes some of the work we're doing here.
In 2016, we came with the idea of trying to measure spread rates in a uniform fuel under high wind speeds. That's something we just couldn't do prior to coming here. And that then got us thinking about some of the fundamental science that could be gotten here by looking at wind-driven fire. And the idea of looking at fuel breaks or discontinuities in fuel, again, we can test it at our facility, but it was a logical partner to pair up with IBHS, and we wrote a proposal through CERTUP to look at, and CERTUP, they, among other things, they oversee Department of Defense military installations, where fire is very much a part of. And they're actively seeking fire research that can be applicable on their lands, and so this proposal is being funded through CERTUP. And the outcome, in addition to being applicable on Forest Service lands and federal lands and state lands throughout the country, will really, it's also targeted to how can the military use this research, because they invest a lot of their time and energy dealing with fires on military land. And this is really specific in funding, and the proposal was written to improve Department of Defense lands, but Department of Defense lands boundaries aren't recognized when it comes to Park Service, Forest Service, state lands. It's just very applicable research regardless of where the fire is. But in this specific example, I would say management and operations and practitioners they're seeking this type of information. This is highly valued, and it's very applicable, and it can have immediate impacts. The next step for us is going to be, in addition to following this up with some different experiments along these lines, would be to analyze our data and publish our data not only in scientific journals, but also in management type applications, and then to communicate that through the necessary. There's a network of ways to communicate evolving research and how it can be applicable to the field. It's fairly well established how that process works, and so literally this could be useful within a year or two, if not sooner.
Together we will find solutions to help drive down the impact of these wildfires that we have seen far too often impacting communities across North America, as we've said. And now we're joined by one of our wildfire experts, Dr. Faraz Hedayati. Faraz, thanks so much for joining us today.
Glad to be with you.
Yeah, we're excited to get some of your insight on how tests like this work. You've worked with IBHS for quite a while, but it's a unique opportunity to be here looking at wildfire in this facility.
That's correct, because, IBHS, first of all, you can see the fans in the background. It's like 40 feet wide, 25 feet tall. You cannot find this elsewhere on this planet.
Yeah.
It's a unique opportunity for us researchers to work here and to look at the interaction between wind and fire at the same time, which we can talk about it later on. It's pretty impressive to be here, yeah.
Yeah, so for us, let's take a step back. Let's go back to where IBHS wildfire research started. How did we begin? What was our kind of initial plan of attack to start working this hazard?
Yeah, so basically, if we want to talk about wildfire hazard, we can put it in different segments. The first one, it can be the hazard part. Well, how hot or how tall the flames are, how fast they can grow. And what we see here is part of that question. And the interaction between wind and fire. So this is a part of our research. The other part of our research is to look at the resiliency of the buildings, building components, and especially full scale. So we don't scale down. We look at a full structure, full deck, and burn them on daily basis when we have wildfire tests here and look at the vulnerabilities and provide recommendations for those.
So while so many people may have seen a picture or a video of our testing, and we love those visuals, you are collecting so much more data during tests like this. Talk to us about some of that data that you collect. I mean, we're talking a ton of data that's collected during every single test.
Yeah, that's correct. So we basically look at temperature, heat fluxes, and also IR cameras, so radiometry, and then machine vision. We analyze the videos to see like the flame profile, the flame behavior, all of those, and talking about big data basically, because we need to have good resolution, record videos at high res. It's enormous data files. Yeah.
Yeah, so I mean, as a scientist myself, like one of the key elements is taking all that information that Faraz just mentioned, turning it into the analysis, looking at what variables matter. Faraz, a lot of our work really focused initially on embers and how they attack buildings. How did some of that essentially make its way now into guidance for homeowners and kind of the best practices of what to do to defend against embers? And we'll get to the flame spread side here in a second.
Yeah, so basically on the ember side, IBHS has gone through different ember generators. We changed the design to create realistic embers. And our knowledge about fire was mostly about flames. Until 2011, where IBHS and FPA and other organizations were advocating for the threat of embers and how we should consider them. And I'm very glad to see that right now NFPA 1134 actually has included embers. So we have seen that in practice, building codes, now we require mesh on the openings that embers don't get in. And I can see in future, we see more of these transitions from flames only to flames and embers.
Research translating into action and things that homeowners and firefighters can use as information that is needed to fill some knowledge gaps.
Yeah, so if you've out there and heard about defensible space or the 0 to 5 home ignition zone, a lot of the work that took place here and through the science community became that. So if you're interested in seeing how all this work actually turned into actions for people, please check out our disastersafety.org/wildfire ready. You'll see some of those elements that actually show you what to do, some of those key actions to take around a home or a business there, that a lot of the work that was done here in the past that's moving forward now, that the science and engineering communities are doing across the board, all our partner organizations, it all makes its way there. And that's where we turn science into action. We use data-driven decisions. What are the best options? What's the best probability to give a home or business a fighting chance against this kind of hazard?
That's right. So much of the time, it's small changes that make a big difference. And this big facility gives us a detailed look at those small details.
Yeah, that's exactly right. So, Faraz, I'm going to turn to you now. As we look at flame spread now, what are some of the factors that we have to consider in terms of how we evaluate how essentially flame spreads through fuel? What's the impact of wind? Say those kinds of things.
Yeah. So flame is basically a gravity-driven thing. It's always vertical. A fun fact, if you look at International Space Station, they have a candle. The flame is not vertical. It's just a hemisphere. So it's gravity-driven, right? So it always goes up, and when we add the wind component, it lays down on the fuel. And it gives it more oxygen and makes the fuel more dry. So, the fuel is more susceptible, and the flame can grow rapidly through a fuel bed with wind.
So that's part of what we're going to be looking at today, right? We're looking at how flames could cross a fuel break.
Yes. So basically, we have two fuel beds here. One of them is the source, the other one is the target, and we add the wind component again to this. And we want to look what should be the width of the gap that the fire doesn't breach over. And this can be used in real world, as Dan mentioned in the video.
Yeah. Some details that we have to pay attention to as we get set up for test number 1.
What a great segue there, Faraz, taking us into what we're essentially going to do today. So some pretty cool live science stuff that's going on, but we've given you a little bit of the why background here as to why this stuff matters, where it goes, how science can actually benefit all of us, all of our homes and businesses.
And how we use science every day to help inform those recommendations that we give to homeowners and we give to firefighters and we give to code officials and we give to all these different stakeholders who want to see more resilient communities.
Absolutely. It's a lot of partners all working hard together. There's a lot of people whose sole goal really, not just here at IBHS, but across the science space and all our partners who really just want to make the world a better place and make a contribution to really, like we said at the Open, to help stop that cycle of destruction displacement that we see that comes from these events.
Absolutely. You can hear the passion in the voices of so many of our scientists. Ian, a renowned scientist in his own right as well, and joining us as one of our hosts today. So I think without further ado, we should check in with Armand and see if we're getting close to being ready for test number 1. Armand, you're standing by with a little bit more.
We are indeed getting close to test number 1, Christine and Ian. Thank you so much. I want to bring now in our research engineer and our wildfire expert, Dan Gorham. And we're getting close to test number 1. First and foremost, why does this testing matter so much?
Yeah, this testing is quite important, and that clip from Dan Jimenez from the U.S. Forest Service, I think, explained it well. This is the fundamental building blocks of what we understand how fire spreads. And Faraz talked about fire spread phenomena and the theory behind it. And what we're doing here in the lab is putting that theory to the test. And what we're able to do at IBHS is that realistic aspect. And Christina and Ian were talking about this. When we think about scientific research, it's really important that our research is repeatable. That is, we do something once and we can get similar or the same result with the same conditions multiple times. It's reproducible, and that is the research that we do here at South Carolina with the same conditions can be reproduced, say, in Seattle, but really emphasizing what we do here at IBHS with the full-scale capabilities, and particularly with the wind, is that realistic component. And so we're burning pretty large amounts of fuels. The pine needles are going to create some pretty hot and short intensity fires. And that's really important for the realistic aspect as we start to understand, again, the fundamental building blocks and develop those models and better understanding to be more resilient.
Give our viewers a sense of what we're looking for them to walk away with here today.
So what we're going to see in this first test is we're going to see a line fire started at the leading edge. We have about a 20-mile-per-hour wind, and that fire is going to spread through what we call our source fuel bed. It's about 40 feet long, 12 feet wide. We're going to see fire spread that 40 feet in under 10 seconds. I'd estimate maybe 8 to 9 seconds. And then it's going to reach a gap. And that gap currently is at just under 4 feet, about 3 feet 11 inches, or in metric terms, 120 centimeters. And what we expect to see in this first experiment is that fire to bridge. We're going to see the flames licking across the gap and to ignite the target source. And so in this 120 centimeter gap, we expect the fire to spread. In the second test, we're going to increase that gap size, and we're going to see what happens then.
Are we ready for the first test?
We're ready to go. I'm going to get started here.
I'm going to let you go. And I will backpedal here and get out of the way so you folks can see everything that's going to take place. And this is about to happen. I'll put on my eyewear here. You are looking as we slowly show you the source bed and the target fuel bed. We are close to that first test. I will step back, put on my eyewear, and off we go. As you can see, we are starting the fire now, and off we go. As you heard Dan mention, moving across that source fuel bed. Dan said in around 10 seconds or so. Timing is everything when it comes to science. As you can see, that fire is quickly moving across that source fuel bed. Those pine straws are feeling it right now. And that fire is pretty much consuming that source fuel bed, those pine straws. And now we're looking at Willits Bridge. We're expecting it to. It is coming across that fuel break. And there you have it. We've got the flames on the other side from the source fuel bed to the target fuel bed. We got a thumbs up from Dan Gorham there. And I just heard Dan say perfect. So we got exactly what we were hoping for in that first test, exactly what we were looking for. Science is an amazing thing, and sometimes you get what you expect, sometimes you don't, but the thrill is examining the process and seeing exactly what happens at the end of the day. Got another thumbs up from Dan, which is always good news. There you see it from the source fuel. 3 feet 11 inches is the fuel break and the target, and look at that. Flames continue to tear across the target fuel bed. 12 by 40 for the source. about 12 by 4 for the target fuel bed. We hope we're giving you a pretty accurate sense as to what we're able to do here at IBHS when it comes to wildfire research. It's amazing too, just in a short amount of time, this is the impact Mother Nature can have on homes and businesses. And this is what drives why we do what we do. So the flames are continuing now across that target fuel bed. And just like that, all that preparation to get that quick result. And as I mentioned, got 2 thumbs up from Dan Gorham, our research engineer and our wildfire expert. This was pretty much expected for the first test. That second test, we are a little bit more uncertain as to whether or not we will see that. You heard Faraz, Christina, and Ian mention earlier, but that's the fun of science. That's the reason we come to work every day and do what we do. We're trying to figure out how science can reach communities and create more resilient homes and businesses and allow people all over the country to live healthier, better lives and safer lives. So the flames continue. And we are pretty much done with the first test here. As we mentioned, stick around for that second test. There you have it. That second test is coming up in just a few moments. And the crew now will start to prepare for test number 2. Let me come back on camera here and just talk to you folks for just a moment. So there you see it. We got what we were hoping for with the first test. Got a couple of thumbs up from Dan Gorham. 3 feet 11 inches is the gap for the first test. 4 feet 3 inches is the gap for test number 2. We're looking forward to it on our number 2 as we start to prepare for that. And I'll talk.
Thank you, Armand. Yeah, so 4 inches is going to be the difference between test 1 and test 2. Now, Faraz, what we just saw was that fire jump over the fuel break. Was that expected, and what does that mean?
So basically, when we add wind component to the flame lays down, and it stretches more than the condition that we don't have wind. So when the flame could touch the target fuel, well, we had ignition, and that's basically what we saw. And I want to point out for the next, if you look at how the flame behaves, it's like fingers, just like this. There are a lot of science behind that we want to model here.
Impressive there for us. And one thing you mentioned, the wind. The wind here was about 20 miles per hour. So that's not a tremendously strong wind. It's just above idle for our fans here.
Yes, correct. So we can start from 12 and go all the way to 120 miles an hour. So it's on the lower end.
Yeah, and if you think about the complex terrain environment that a lot of wildfires take place, there's a lot, there's more winds that are ongoing. This is just one component of this test. And like I mentioned earlier when we started, we've been doing this for a couple of weeks now back here, looking at all these different scenarios. And we're just using the 20 mile per hour scenario here as an illustration in this particular test series to look at that. And now we're going to stretch that gap a little bit more. But the point that always strikes me after watching several of these, how fast this happens. And you think about if you're in a home and you're asked to evacuate, look how fast that fire just spread back there. When fire in a wildfire starts to impinge on your area, please take action. Please pay attention. You saw how fast that just happened. That's how fast this can go in real life. And under even more extreme wind conditions, you're adding all these things. We mentioned embers at the start. This is all playing out in real time in very, very fast motion.
Absolutely. And right now we are using pine needles as our fuel. But for us, that's just an example of a fuel. That there are many things that contribute to fuels out in a wildland.
Yeah. So basically, about 30 to 40% of fuel in Australia, I was reading about this study, is pine needles and surface fuel. So basically, a large amount of land is covered by this type of fuel. In addition to that, these small fuels and low-density fuels are very susceptible. When they ignite, they can preheat larger fuel. And then, this chain reaction could go on, and then we see ignition of buildings, of tall trees, and all of those big fires. So this is a very important piece to understand fire spread.
Yeah, and you can see now the team behind us working towards setting up test number 2 for you. We're going to show you another fuel break test. This time, the only difference is going to be the width of that fuel break. We're going to add 4 inches, so from 3 feet 11 inches to 4 foot 3 inches. We're going to see what the impact of 4 inches can do.
That's right, and we go, essentially these small increments by small increments, looking to see what is the change in the outcome that happens. And we also make tons of measurements. We're measuring temperature. We're measuring the amount of energy that's imparted on just small square areas to understand. As Faraz mentioned, modeling. This is how we essentially get computers to simulate this stuff. And we can run thousands of those simulations and start to understand what are the probabilities that a fire would jump a fuel break, how the flame itself behaves. We can turn that into looking at how houses can ignite. And ultimately, we're going to use science to solve that problem.
Ian, a great point there. Science is in our everyday lives. And for a lot of people, science may just be, something you learn about in grade school, the scientific method. But the scientific method is something that's on display here at IBHS every single day.
Yeah, it's the repeatability aspect, being able to repeat an experiment, turn it over to somebody else to even run something similar, to model it, those kinds of things, and documenting your results and making sure you can repeat it. Sometimes there are tests. There are plenty of tests where we have no earthly idea what the outcome may be, but you have to start with somewhere, and that's how science works. You have an idea, you have a hypothesis, and you go test it. You take one variable, as I mentioned, at a time and start to work the problem.
Today, that variable is the width of the fuel break. Now, another thing that we want to talk about today in regards to that fuel is we're here in Richburg, South Carolina, but we can reproduce conditions that are like the conditions of fuels in California. Faraz, talk to us a little bit about how we do that.
Yeah, so basically behind the camera there's like a big kiln that we put the fuel there, and it could be pine needles right now, or larger fuels like decks or different building components. We put them there, dry them for a certain amount, and there is like a very complicated scientific process, how long and at what temperature we condition them. And a few minutes prior to the test, right now, we just bring them here, put the fuel there, so we eliminate the humidity of South Carolina from the wildfire behavior.
Our dew point today here in Richburg is up in the low 70s, so it's a bit warm in here in the test chamber, even without the fuel burning.
Yes, it is. It's been a warm set of days here in the Carolinas, and we've dried our fuel. The fuel, as Faraz mentioned, that's how we condition it here. In terms of air mass, what comes in the chamber is essentially what's outside. That's what's coming through the fans. This is what you would call, it's an open air wind tunnel. It's not a return flow like some of the scaled wind tunnels are. That's how we generate, enough flow that we can do here when we're up at 120, 30 miles an hour. So, so what comes in is coming through those fans. So we take every degree on the other side, as Faraz mentioned, to use the kiln setup to basically condition, even if we're putting a full deck assembly into a kiln, to be able to basically mimic those exact characteristics. We don't have to go to the exact spot out in the West to do this. We have the means and the tools to be able to make that happen.
And then with the magic of the IBHS large test chamber, in a couple of days, we can flip around and recreate a hurricane in here. It is an incredible place to work, and some really passionate people here.
Yeah, that's exactly right. And you see the guys working behind us. A whole team of folks actually supports all the experiments that goes on. Not only just the science staff to our production team, the technician guys, everybody that's out there doing a lot of work that makes all this happen. It's not just one person running an experiment.
You can see how detailed the guys are about how they lay down the pine needles. This isn't just pine straw tossed across a fuel bed. This is very detailed work that they're doing to create these reproducible tests.
Faraz, tell us a little bit about, we actually weigh all the fuel. That's what's going on actually right immediately behind us. So tell us a little bit about how we set that up.
Yeah, so basically we want to have a uniform fuel load and uniform packing ratio. So basically what we do right now, we weigh them before, we lay them down, and then we try to uniformly pack the fuel, because the porosity of the fuel is very important here in how the flame burns the fuel and moves forward. So basically that's what we're trying to do right now.
A whole team helps make that happen. And as they work on setting up for test number 2, again, we're going to bring you one more test with a fuel break of 4 feet 3 inches coming up here. So feel free to share the stream, to share this work with other folks as we continue on through our broadcast. We want to check back in with Armand Brody. He is once again looking at how this setup works and showing you some of the behind the scenes of how, in between the action that everyone likes to see, that fire that inspires us and really gets your attention on social media, how all of that is made possible by a whole team behind the scenes. Armand, over to you.
Dan, one more time, real quick. We'll get to Sean as well in just a moment. We mentioned Sean earlier, our construction and facilities manager. Dan, I just wanted to make sure that you were able to give us a brief summation of what we just saw and the significance of it in the first test.
Yeah, absolutely. So that first test went pretty much as perfectly as planned. And when I say planned, I mean it was repeatable of everything we've seen thus far with this testing. We've been doing this testing for about a month now, and we've been doing these kinds of experiments for that amount of time. I think we've done 30 or 40 tests. And what we've seen is at this fuel condition, this wet fuel at the high wind speed, about 20 miles per hour, and at the 120 centimeter gap, the flames from that source bed are just long enough. They can just touch the target enough to ignite it. Now, you'll see at the end of the test, we saw those big clumps of pine needles come over. That's not what we're looking at. That might be described as a mass transfer or the embers, which we know are really important. But for this fundamental research, we're really just trying to focus on that heat transfer, so just the thermal energy from the flame. So we saw that flame tip just barely touch at the center. I thought it was going to ignite right then. It didn't. And then maybe 5 seconds later over the side, again, we got another flame contact, and that was enough to ignite these fine fuels. So it was a good test. We're getting set up for test number 2 here now.
Thank you so much. I'll let you go. Let's bring in Sean now as the preparation continues. As you can see, our crew is getting those pine straws ready. Hello, Sean. How are you, sir?
Doing well.
Good to have you with us. I want to talk about sort of the process. So Dan has talked about the why of this whole thing, but really walk us through how we prepare the fuel process. Let's talk about that.
So the researchers have asked us for a fuel load of approximately 2.5 tons per acre. So we broke that down to 0.56 kilograms per meter squared. And the carts here are 12 foot wide. So 2 foot section, 12 foot wide equals about 1.26 kilograms of fuel. So we dry that in a kiln, and then we bring it in and weigh it, and we identify an area of 2 foot, and then we fluff it and spread it in that area.
How do we execute the test?
How do we execute the test?
Yes.
You mean with the gas igniter?
Yes.
So that's the process. There's an igniter. It's a bar that has natural gas running through it, and then it's lit so that we get a consistent ignition across the entire width of the cart of the fuel. So once that we want it to ignite consistently across the whole thing so that it moves in a pattern. The length of the cart is 40 feet. So once the fuel is ignited across the cart, it moves up in the direction of the wind blowing, and we get a consistent burn.
Thank you so much, Sean.
Is that right?
Sean McComber, our construction and facilities manager. We got his thoughts as well. The preparation continues behind me. They are strategically, meticulously, and accurately getting those pine straws set on that source fuel bed for the second test. The updates will continue. We'll send it back to Christine and Ian at the desk.
Thank you, Armand. Math and science at work right behind us. It gets me excited, Ian.
Oh, I love this stuff. I love it. I love it. And we get to show it to you at home. And I hope you're enjoying our broadcast today as we look at our IBHS wildfire fuel breaks testing. You get a behind-the-scenes look here at what we do. Not often is it every day, but it's a lot of days. And as you can see, there's such a passionate group back there. Everybody's working really hard. They've been working really hard on this whole test program over the last several weeks.
They really have been, Ian. And we want to take some time while we're getting set up for that second test. Again, coming up here in just a few minutes, as soon as the test bed is ready, we'll bring you coverage of a second wildfire fuel breaks test here at IBHS with a slightly larger gap than what we had in test number 1. But we really want to talk about how our research happens, and part of it is so much the people behind it. It's a passionate group here at IBHS. If you can't tell from just Ian and I here talking with you today, we've been talking with Faraz as well and Daniel, the whole team, a really passionate group.
Yeah, and you've heard from a lot of folks too, and again, I mentioned the Forest Service earlier, a big partner on this particular project. So we're gonna take a look again at our second package with Dan Jimenez. Dan's been back there. Dan actually did the ignition on test number 1. That was Dan Jimenez from the Forest Service. So let's hear what Dan has to say as he kind of explores a little bit more deeper about what we're doing in this test series.
Fire behavior research happens in a laboratory setting, at least from an engineering. You can identify mathematically how you expect heat transfer and combustion to behave, and you can test those theories in a laboratory setting But again, you know, you're limited, we're limited until, as to what we can do at our facility. So what we're really looking at here is, you know, there's a lot of money and work being done to develop buffer zones or fuel breaks in various communities or values at risk, but we don't have a lot of science and data supporting how effective or how big those need to be to actually act as a fuel break, to effectively suppress fire or act as a bridge, an unburnable bridge between vegetation. And this study is really looking at how big of a gap can fire span under different fuel loadings and fuel moistures in wind fields. So we're really targeting that with this facility, is instrumenting gaps and then measuring whether or not fire bridges it, and then refining that measurement, you know, that distance. It's nothing like this has been done before. I think we're all stunned at how reproducible, which when you take the scale into account, that just adds to the complexity and how surprising the results are. In other words, the data that we're seeing is showing small changes in gaps show the exact same result in fire behavior. So that tells me that the fuels that we're using are very consistent, which is expected. We're using a homogeneous fuel. The moisture is the way we're conditioning them is highly reproducible. And ultimately, I mean, the most surprising is the wind field is so reproducible, which is, you know, it's exciting to see it, and it just makes us all think about future work that could be done here, because you don't get that often. You really just don't have the ability to reproduce wind flow and wind fields and get repeatable data like that consistently, and so it's an awesome facility.
Ian, this data is so unique that we are able to capture here, and it's because of an investment by the insurance industry to help us make this science possible. It's amazing to me. We talk about, and we hear our wildfire guys talk about it all the time, fire has always been a part of our ecosystems, yet there's some of this data that we've just never been able to capture before.
That's right. Science is catching up. And if you look at some of the other natural hazards like hurricanes, tornadoes, even hailstorms, looking back at those kinds of things, we have a lot of research going back decades and decades and decades. Fire science is racing to catch up now. Yes, we've had to live with fire, and we have to. It's part of our ecosystems for sure. And now we have communities that are kind of impinged on that. And we need to figure out what the adaptation solutions are. And all this work plays there. That's one of the key components of it, is to be able to take that science and turn it into that kind of action. And that's what all this work is going. You see the guys behind us, they're loading up more fuel into the bins. They actually weigh it back there behind us. But yeah, this really does hit home, especially if you look at the fires of 2017, 18, and what is actually ongoing right now, you know, today, that we've seen even over the last couple of weeks.
Absolutely. It's tragic seeing all of these communities impacted by fire, and that really just adds to the drive here at IBHS to continue this work with our research collaborators to find these solutions that we need.
Yeah, that's exactly right. And it's a great group of people working very, very hard. And you've gotten to hear from a lot of them today. So we're actually, we have a couple of really cool packages coming up that take you a little bit behind the scenes of who our scientists are.
Yeah. So we're going to start with one of our wildfire experts who you've heard a little bit from already today. We're going to take you a little bit deeper into meet Daniel Gorham.
My name is Daniel Gorham. I am a research engineer at the Insurance Institute for Business and Home Safety. My work focuses on studying and understanding how perils, and particularly wildfire, impact the built environment. And what that really means is we try and study and understand, and in the lab recreate how homes are ignited and otherwise damaged by the flames, embers, and smoke from wildland fires. So my work into the research that I do today really stemmed from my childhood of wanting to be a firefighter, and I achieved that goal when I was 18 years old. I joined the Baltimore County Fire Department, and I was a volunteer there for 8 years. And the fire service was great to me. I learned so much, but I still had this drive, desire to understand it more. And so I went to college for engineering, and fortunately found the combination of fire and engineering and fire protection engineering. And then to translate from what we generally think of fire protection engineering, this is fire inside the box, sprinklers, fire alarms, smoke alarms, evacuation. I looked at fire outside the box, and that was wildland fire. And so for my grad school work, I worked with the Forest Service looking at how fire spread through fuels, and the hypothesis was it wasn't the big wall of flames, but actually the intermittent flame contact. And so I studied at the lab in Missoula, Montana, and looked at that, and now here I am today, looking at how this peril wildland fire impacts the built environment. So the full circle of riding a fire engine, responding to home fires, going to school for engineering and understanding the science of it, and now putting that all into practice. So studying fuel breaks is important because fuel breaks and the discontinuity of fuels, as we think about it from an engineering term, is important to understand and maybe not predict, but forecast how fire might spread over the landscape. Fuel breaks is essentially a technique that can be man-made or natural, and it's breaking up the continuity or altering in some way the fuel. So this might be as simple as just trimming some trees and using specific fuels in an area to affect the fire behavior, but it might be as drastic as coming in with hand tools and bulldozers and scraping down to bare mineral soil like firefighters will do to stop and suppress the fire spreading. And so studying how fire spreads through these discontinuous fuels or fuel breaks is really important to this fundamental understanding of how fire behaves and how we as humans can affect that to reduce the losses from it. This project is a really special one, close to my heart. I did my graduate school work at the Missoula Forest Service lab out in Montana, and this is a collaborative project where we're working with researchers from Missoula as well as other Forest Service, including the Southern Research Station and collaborators from Tall Timbers in Florida. And so it's a really important opportunity for me and my colleagues to learn from other leading researchers and scientists in the field. And these are people with direct on-the-line experience in firefighting and a different perspective on how wildfire behavior acts. And so we're learning a lot, we're able to contribute a lot, and this is really highlighting the unique capabilities of the IBHS research facility. And when our researchers were here just the past couple of weeks, they were able to see and were awed essentially at what we're capable to do. And we see so many more opportunities to continue this relationship, this research collaboration going forward. What do I like to do in my spare time? So I'm recently a dog owner, our pup Feta, and so I spend a lot of my time thinking about her and playing with her and taking her on long walks. But here in the Carolinas, I really enjoy being able to go to the mountains one day and the ocean the next. And so being outdoors and enjoying the weather, particularly after being inside for the past year, has been great.
Daniel, one of our two scientists who are focused on research, part of the whole team of researchers here at IBHS.
Yep, really good story there, taking a look at behind the scenes of who Dan is, and you'll hear a little bit more from Faraz later on.
That's right. Before we meet Faraz, though, we want to go check back in with Armand Brody. He is standing by with an update on how the setup is going for test number 2.
Christina and Ian, thank you so much. We are coming very, very close. I just looked at Dan. He said about 5 minutes. And that was about a minute or so ago. So we are coming up on it for that test number 2. Our crew has done a wonderful job of getting those pine straws ready. They're so meticulous and so strategic with it. It's quite a thrill to watch. But we're just about set for that second test. I'll toss it back to you guys very quickly.
Thank you, Armand. A huge shout out to our team behind the scenes, our carpentry staff, our technicians. They're all the ones helping make this happen. They do it every day. You may not see them on camera with us, but they truly are what makes it all happen.
Yeah, great group of people working hard back there. They're doing that every single day as we work to go through all these full-scale experiments. These are big projects. They're here for weeks and months at a time, not just around wildfire, but think about hurricanes and winds. If we're testing a full-scale home that's out there for wind, or looking at shingle vulnerabilities on an actual house here in the big chamber. These are big projects. They stay in here quite a while, and we do lots of work with them.
And while this project is going on in the test chamber, the carpentry staff, our technicians, they're working on building the next building outside so that we can keep the research moving, so that we can get to those solutions that these communities really need.
Yeah, that's exactly right. All this research turns into action and science. So I want to take you a little bit, again, we're going to do another package here behind the scenes of who our research staff is. You heard from Faraz earlier. Faraz provided us some great color commentary to go along with all our work today. But now we're going to show you a little bit about who Faraz is, and take a look now.
So my name is Faraz Hidayati. I'm a research engineer at IBHS. My job mostly is about connecting computer science to different perils, including wildfire, hurricane, and hail. The first time I visited IBHS, I was a PhD student at UNC Charlotte, and my advisor at the time was a friend of Dr. Steve Coles, and there was a project about embers here happening, and I visited IBHS, and as soon as I got in, I was impressed by the fans, by the experiments, by everything. And then I chose that to be my PhD thesis. So I worked on that for 3 years and worked with IBHS during that time from 2015 to 2018. And then 2018, I became an intern. And then 4 months after that, something like that, I was a full-time employee. As I mentioned, my PhD dissertation was about embers. The first 2 years I worked here, I was heavily involved with characterizing the ember generators here, working with our production team and our instrumentation team to create realistic embers. Well, and count how many embers we can generate by each design, ember generator design that we have. So that's one part of my research here. The other part was look at different components of the building. For example, decks, siding, windows, both on theoretical and experimental parts. I researched those components. So fuel break is basically fire spread from a source to a target. The source could be a house, a shed, a tree. In this case, it's pine needles. And this project is funded by US Forest Service, where they want to know what should be the width of the fuel break. So basically, with mechanical operations, they remove the fuel around the community and then expose that to different wind speed, to different humidity, to see what should be the gap that the fire doesn't break, so it doesn't basically jump from one side to the other. And that's what we're studying here. We look at embers, but for the most part, we look at flames and how the flame the flame profile basically changes with wind and when it touches the fuel on the other side of the gap.
Another one of the incredible minds here at IBHS helping drive this research and helping us find these solutions in the large test chamber.
Yeah, you can hear a little bit of the audio. We got the fans going again. We're getting ready for test 2. We're going to show you a little bit of the scale of what this building is as we get ready to take on test number 2. So we're going to bring back Armand Brody. He is perched himself on a very unique spot in our facility. So we are going to send it back up to Armand here shortly to just give us kind of a sense of scale of what the test chamber looks like. Armand.
Thank you, Ian. Wow, is all I can say. As I look around to my right, and then I look to my left, it is cavernous and attention-grabbing and gaudy, but this is what we do. This is the investment that has been made here by the insurance industry for this kind of a facility. So just sort of take it all in here. Hopefully you're able to get some different looks at what we come to work for and with every single day. I got some thoughts from one of our scientists. I wanted to get the perspective of one of our scientists about what we really do here in this chamber. And he mentioned a couple of things. He said that this chamber allows us to have our curiosity thirst quenched, talking about how we can solve these construction issues to problem solving and how to accurately measure something. That's one thing. Also mentioned a sense of purpose, people looking to help their communities, which is really what drives what we do. Talking about building construction professionals who are looking to improve techniques and just make that impact in the community. And we get to come in here every day, and our scientists, our team, we can come in here and push buttons and play around. And as you heard Christine and Ian, who are 2 meteorologists in their own right, talk about how weather can't be controlled, where there are some things, some variables in this cavernous chamber that we can control. And so that's what really makes working here so cool. When you look at this enormous facility, 21,000 square feet, 6 stories tall, 145 feet wide by 145 feet long. Take it all in. It is captivating. I've been here 8 months now, and I've still not really had the opportunity to take all of this in. It is quite a treat. And it's quite a thrill that we get to come to work to this kind of facility where we get to do this great testing that we know is going to impact communities. It's quite a thrill. So Christina and Ian, I hope we've given our viewers sort of a scope of what we can do here with this chamber as we get set for test number 2. I'll toss it back to you guys.
Thank you, Armand. A unique perspective here in the IVHS test chamber, and it still gives me chills every day driving up to work. You see that wall of fans and just knowing what this place is capable
Yeah,
of.
pretty cool place. We brought back Faraz in here. We're getting ready for test number 2, so we're starting to ramp up. We're going to get ready to go here any moment. So, Faraz, we've got our wider fuel break. What do you kind of think might happen here with this one?
So basically, this fuel gap is a few inches wider. So what we think is that the fire doesn't bridge from the source fuel bed to the target fuel bed, but we don't stop there. We repeat each and every experiment that we do when we see a result to make sure that this is a repeatable pattern, and then we report the data.
And again, it's the flame we're looking at. We'll see some embers flying around, but in this case, we're looking at the flame.
Correct. So this is basically what we want to know: the effects of wind on the flame and how much the flame can stretch under different wind conditions.
We're keeping the wind, though, the same from test 1 to test 2. We're still at 20 miles an hour. It's just the distance of that fuel break that we're going to change. So what do you say, guys? Should we get test 2 going?
Yeah, I think we're good to go. I got the thumbs up from Dan Gorham back there. I see Dan Jimenez standing by back with the burner. So I think we're going to good to go. We're going to toss it to Armand. Going to take us on play-by-play here in a second. So Armand, if you've got us, take it from here.
We are ready for that second test. Dan is standing right by me. Dan, give us a quick preview.
Yeah, so the difference between test 1 and test 2, which we're about to start right here, is 10 centimeters, so just about 4 inches. And so that source, or pardon me, that target is just 4 centimeters further away, and we're going to see whether or not that 4 inches is enough that the fire doesn't spread the gap. We're ready to get started for test 2.
Let's go. Here we go. All right, I will get out of the way here. And here we go. I'll put my eyewear on again. And off we go with that second test. As you heard, 4 inches difference, 3 feet 11 for test number 1, 4 feet 3 inches for test number 2. And here we go. Source fuel bed now being consumed by these flames. We will see if that bridge that you've heard Faraz and Dan mention, we will see if we get the bridge that we're looking for. Fire moving quickly along the source fuel bed, as we expected. I'm looking at Faraz, or rather Dan here, now coming up on the fuel break itself on the gravel. And now hopping across to that target fuel bed. So we see fire impact, not just on the source fuel bed. We also see it on the target fuel bed as well. Just a brief amount of time these tests take place, but that's all it takes. Also noting the fact that in science, every little inch matters. Those 4 inches, that's what we're examining from test 1 to test 2. You can see the wind now blowing what's left of the fuel. And we see fire impact not just on that source fuel bed, but also on that target fuel bed. Even the fuel break itself, the gravel, feeling some of the impact of that fire. Flame continues to burn on the target fuel bed. There you have it. We were a bit uncertain what we would see with this second test. But yeah, the fire is licking up much of the fuel on that target fuel bed as those pine straws feel the weight of that fire and the 20-mile-per-hour wind speed. We hope you're getting some pretty good looks at this, folks. Fuel breaks live. Nothing quite like this we've done, especially in the 8 months that I've been here. Dan, let me get a quick comment, if I can, from you here.
Sure. So we had about 10 centimeters more in the gap, but one of our observations is the relative humidity here in South Carolina actually isn't too high today, and we had the fans basically blowing over the fine fuels, and that fine fuel means that they can absorb moisture really quickly, but they can also lose it. So this was probably more like a dry fuel test than it was for a wet, and at that condition, we expected the fire to bridge the gap.
And so there you have it. Test 1 complete. Test 2 complete. Let me walk back over as we get set to wrap up, or at least I do. There you have it, science at work. It's what we do here at IBHS. And I hope I've been able to sort of walk you guys through what we do from a field reporter perspective. Christina and Ian, I'll send it back to you.
Problem solving every day. That's why we run these tests. And that is what drives our work, solving problems so that communities can be more resilient.
Yeah, pretty cool 2 tests there. You saw Armand's, his fire suit flapping in the wind out there about 20 miles an hour. Good point that Dan made. Kind of a low-end relative humidity day here in the Carolinas. So, Faraz, I'm going to turn to you a little bit and talk a little bit about some of the tests that we have done where we didn't actually see some of the flames jump. What were some of the conditions that actually resulted in essentially what would be a successful fuel break?
Yeah, so basically we have 3 knobs to play with here. One of them is the fuel moisture, wind speed, and the gap. So basically the drier the fuel, the more susceptible it is. The wider the gap, well, it's less likely that the fire jumps over. And wind, always a stronger wind means longer flames. So basically when we play with these knobs, we can optimize based on these parameters that what should be the gap. And what we saw here is basically modeling Mother Nature is the most difficult thing that any modeler can do. So I've done modeling my whole life. Modeling fire and Mother Nature is very difficult. And as I mentioned, we need repeatable patterns, and we repeat every test, so we don't stop here by one test.
Predicting Mother Nature is quite a challenge as well, if the meteorologist can weigh in on Mother Nature as well.
That's right. Trying to forecast the weather, we use the same techniques. It's all computer mathematical equations built into computer programs in a very basic kind of sense that are meant to basically produce a prognostic, a look forward at what that could be. And we do the same thing here with understanding the physics of flame spread and how flame reacts to wind flow conditions, whether there's barriers, complex terrain, all those things. It's a lot that's going on, and that's how we actually push the needle forward and turn science. Ultimately, we get these results, we figure out where the probabilities lie and turn that into guidance.
Absolutely. An incredible day for us here at IBHS. We are proud to have brought you a live look inside our research as it happened. We hope you learned a little something and enjoyed seeing science at work in the everyday world.
Yeah, this was really incredible, and I want to encourage folks out there, if you want to see some of where the science turns into action, go to disastersafety.org/wildfire ready. Also, pull out your mobile device. We have our Wildfire Ready virtual app. It's an immersive mixed reality application that can show you some of these steps in a virtual reality space on your cell phone. So it's available on the Google Play and Apple App Store. Please check it out. You can go through and see what happens to various components around a home when we're put under a wildfire scenario. So really cool piece of technology. If we sparked your interest, pun intended there, on wildfire and some of the science and how it turns into guidance for all of us as home and business owners.
Absolutely, Ian. A great point there. And the Wildfire Ready Virtual will take you to disastersafety.org/wildfire ready as well. It's all interconnected so that you can get the most out of the work we do here at IBHS every single day. Faraz, thank you so much for joining us throughout the day today. We really appreciated your insight. And before we go, a huge shout out to the whole team behind the scenes, especially our producer, Aubrey Marcinko, who is in the director's chair for today, helping us bring this to you. Ian?
Yeah, absolutely. What a day. I'm going to give a couple shout outs here. Malik Cooper, one of our student interns, handling some of the really cool camera work. Lauren Wilson, also on the direction there here in the chamber camera system. All the team you saw behind us, Dan Jimenez from the Forest Service, Sean McComber, his team, David Troll leading the production group, all of those guys. I saw Chris Gay back there, one of our design engineers, Dan Gorham, everybody.
Freddie Bird running the fans for us. It takes a team effort and a huge team here making it happen today.
Absolutely. A great group of people here at IBHS and our partners, and we're just trying to make a difference, trying to stop that cycle of destruction.
That's right. Now follow us along on social media, Facebook, Twitter, Instagram. You can find us there. Keep up to date with all of the work happening here at IBHS. We love to share it with you so that you can see the impact that we are having on communities across the country. And we hope that soon enough we'll be bringing you another IBHS Live. Thanks for joining us.